right. I'll get started here. Oops. I did that update and I swear it's changed my keyboard, or I just don't know how to use it anymore.
Yeah,
like
it looks like it changed for like permanent.
Oh well, yeah, maybe I have a switch to it on, so I can talk to my grandma.
I don't think that's
No. All my emojis, my emoji keyboard. Okay, so does everyone have assignment 2? Yeah. Okay. It is due,
I guess Wednesday.
next Wednesday. You'll always have a week to do it. And so same deal. Through the beginning of class, you can't get it to me. If you can't get it to me, then you have to get it to me earlier, right? Okay. And I want you to do your work on here. It's just a nice 1 leaf, 2 pages, 2 questions. Okay. If you didn't get assignment 1 back, I have them here so you can grab them later. If you want a blank assignment 1, I still have some. If you want to practice, otherwise they're going in the recycling today. And while I'm at it, if you don't have a formula sheet, put your hand up now. Everyone has a formula sheet? Great. Okay. Woohoo. Oh boy. Oh boy, oh boy, oh boy. So we started chapter 3 last day. Okay. Any questions? So we're not going to review chapter 2 just because we're not dealing with it today. In fact, it's not going to come up in any future stuff. So this kind of standalone chapter that I don't like very much, but we got through it. Now you have an assignment. It'll be on test 1 and it'll be on the final. Okay, but that's about it. That's about it. What? Okay, so get 2 of these. All right. Okie dokie. So remember, no labs this week. Feel like I can't emphasize that enough. It's important, guys. Don't go to the lab. Okay. So we started chapter 3 last day. Chapter 3 we said was about the normal distribution. How vague is that? It's a fitting title, but kind of vague, right? So the normal distribution, remember, is the one that looks like this, kind of a bell curve. Okay. And we said, okay, we're going to need some terminology, right? So let's just recap that terminology so that we have it here. So if I say X bar, you say sample mean. If I say mu, you say population mean. Right? So the sample has a mean and the population has a mean, right? We take the sample mean to try to predict what the population mean might be. Right? Same idea. Lowercase s, that's your sample standard deviation. Or a lowercase sigma, which is an O with a tail on top. It's a sigma. That's your population standard deviation. Right. And like I kind of emphasized last day, it's going to be so important to keep track of these throughout the course now. right? We want to keep track of, okay, well, that's the population mean, or that's the population standard deviation, right? Oh, no, we got that from the sample. That's the sample standard deviation, sample mean, right? So we want to be able to read a question and identify where did this information come from. Okay? So then we said something fun. We said, okay, well, here's a fact that under the normal distribution curve, right, before the tails get too tight, right, so the tails, we'll talk about it later, but the tails actually never close. They're open on the axes to negative infinity, positive infinity. Okay, so that's just the fact. Kind of hard to wrap your head around, right? But there's this region of area, right? And then it kind of closes off, and then we don't really care about that area. Okay, but in this open area, we can fit 3 standard deviations on either side of the mean. Okay? So we said, okay, so if we have a normal distribution, I'll draw it first. We have a normal distribution, might look like that. Okay. The normal distribution is centered on the population mean. So I'll just make a note here. The normal distribution is centered on mu, right, our population mean. So whatever happens, if you're drawing your normal distribution, you know in the middle you have mu. Okay. And then, oops, okay, not sure. Can't scroll anymore. Hopefully I can write. And then we said, okay, if we move out 1 standard deviation, 2 standard deviations, 3 standard deviations, I'm trying to make this distance the same for each of these blocks, right? Because that distance is 1 standard deviation. Okay. So here, right, we moved out 1 sigma, 2 sigma, 3 sigma. Okay. So we're talking population standard deviation here. Okay. And same idea on this side, moving out sigma, sigma, sigma. Okay. Oh, this should say centered on mu. Not sure what happened there. We can fit 3 standard deviations on either side of the mean under the normal distribution. So we can fit 3, I'll say sigmas, on either side of the mean before the area under the curve gets too small, right? Then we don't care. Before the area under the curve gets too small. So we can say that, okay, well, here, so we've got mu in the middle. And at this first point, we said that we have mu plus mu minus sigma. I'm on the wrong side. Mu minus sigma, right? I've gone from mu down 1 sigma, so mu minus sigma, right? And then here, this next one, I'm at mu minus 2 sigma now, right? And then I'm at mu minus 3 sigma. So here, we're at mu minus 2 sigma. And here, we're at mu minus 3 sigma. Same idea on the other side, right? We have mu plus sigma mu minus 2 sigma, mu minus 3 sigma. Yeah, thank you. Easy fix. Makes a big difference though. Thank you. Okay, so now we have this fact that we talked about, right? So we can fit 6 standard deviations under the normal distribution curve, right? And so 6 sigma, and I kind of talked about it, no one had heard about 6 sigma, but you will eventually. In business, it's some sort of philosophy, a 6 sigma philosophy. It's just talking about covering everything under the curve, okay? All the possibilities. Okay, so we said that regardless of the mean, mu, and standard deviation, sigma, talking about the population, okay, the normal, we will always be able to fit 3 standard deviations on either side of the mean. Okay. So 6 sigma fit under the curve. Fit under the curve. So that's pretty cool. Right? Kind of hammering it home. So it doesn't matter what your mean is or what your standard deviation is, right? Just how populations behave is that most of this curve is going to be captured between these 3 standard deviations on either side. Okay, so little fun facts, or LFFs. I can even number them. So one fun fact is that these tails, we talked about it, right? These tails for the normal distribution, even though we draw them closing on the axes, right, they never actually close. And so there's always a little bit of area underneath the curve, okay? So technically, these tails continue to negative infinity, positive infinity. So our first LFF is that the tails of the normal curve, of the normal curve or distribution extend from negative infinity to positive infinity and never close on the axes. It's interesting. Why would we care about that? We care about that because the area under the curve is a probability, right? It's the probability of something happening. Okay? So our second LFF is that the area under the curve is a probability. Thinking back to when we first introduced the normal distribution, right? We said, okay, so we plot our data, right? And we make a histogram and we see this normal distribution, right? We talked about heights of males, I think, right? And so we've graphed all of these heights, right? And we said, okay, so here we have some short people, and then most people are kind of in this range, right? And then we have some really tall people, right? So thinking about that area under the curve, right? If you have a peak, then the probability is high that you're in that region, right? And then we have tails for extremely short people and extremely tall people, right? Depending on the situation, right? You can only be, you can't be a negative height, right? But I guess technically you could be infinitely tall, right? And so we say that these tails go to infinity on either end, right? Just allowing for the possibility of finding someone negatively tall or infinitely tall, right? It can still happen. And so it just makes room for those unlikely probabilities. Okay? So that's why it's so cool. Leading us to our third fun fact. Okay? If the area under the curve is a probability and it covers all possible outcomes, then the total area under the curve must be 1. Okay? So the total area under the curve is 1. Right? The total probability of all possible outcomes must be 1. Right? So that's pretty cool. For me, it's kind of mind-blowing, right? We're thinking about these tails that never close, and yet the area under the curve is still 1. Right? That's kind of freaky, but that's just a fact. It's a little fun fact. Okay, so one last thing that is probably the first thing that you would say if I asked you to name some things about the normal distribution. We're not too familiar with the normal distribution quite yet, but you do know that it's symmetric, right? It's symmetric about the mean. Okay? So we're going to use that fact quite a bit. So the normal distribution is symmetric about the mean. Right, because we said from the mean we move out 1 standard deviation on either side, right? 2 standard deviations, 3 standard deviations. It's the same that happens on either end. Right? And so we're going to use the area under the curve to calculate probabilities associated with events. Okay? So we will use the area under the curve to find or calculate probabilities associated with some given event. So now we're transitioning to something like, what's the probability of finding a male that's taller than 6 feet, for example? Right? And so that means that we have to know, how does 6 feet compare to the rest of the population? Right? And so we have this kind of quick approximation. It's called the empirical rule, but I'll just call it the 68, 95, 99.7 rule. Okay? So for like a quick estimate of areas under the curve, right, we're going to use the 68, 95, 99.7 rule. So it's exactly what it sounds. So if you move out 1 standard deviation on either side of the mean, you've covered the central 68% of the population. If you move out 2 standard deviations, you've covered the central 95% of the population. 3 standard deviations, you've covered the central 99.7% of the population. So basically all of it. Okay? So for quick approximations, of the area under the curve, we can use the 68, 95, 99.7 rule. It's also called the empirical rule, but I just call it 68, 95, 99.7 rule because that tells us everything we need to remember. Okay. So going back to our normal distribution, I'll kind of draw a bigger one here, try to. It's centered on the mean. And if we move out 1 standard deviation on either side of the mean, so here we're at mu minus sigma, and here we're at mu plus sigma. This area that's the central 68% of the population, approximately. 68, that doesn't sound approximate. It is. Okay, so here, this area, it's always kind of hard to do a, there we go. So just knowing that, right, we can find lots of probabilities, right? So if I tell you that something is 1 standard deviation below the mean, right, then you know that you're here, right? So your observation is 1 standard deviation below the mean. Right? And so, okay, if you know that this area is 0.68, I could ask you to find what's the probability of finding someone shorter than this, for example, right? The probability of finding someone shorter than this is this area. Right? And so we have 2 things that we can play with, right? We can play with the fact that the total area under the curve must be 1, right? And we also know that this area is 68% or 0.68. And I guess 3 facts that we play with is, third one is that it's symmetric, right? So this area must be the same as this area, right? And so we can find this area, for example. Oops. We can find this area using the facts that the total area is 1, the curve is symmetric, right? And the central 60 or central, yeah, 1 standard deviation on either side of the mean. On either side of the mean captures the central 68%. All right, so we can use that. probabilities, remember, are decimals, right? We work in decimals when we're talking probabilities. So 68% is nice to talk about, right? But we're going to use 0.68. So that means, just drawing out the curve again. You don't have to, I just want it down here. Mu minus sigma to mu plus sigma. So this area here is worth 0.68, meaning that this area combined with, right, both of the tails together, right, must be 1 minus 0.68, which is 0.32. Right, so using the fact that the total area must be 1, and between mu minus sigma and mu plus sigma, we've captured the central 68%. Right? And then, so now we want to know what's the area in the lower tail, for example, right? And we can find that by saying, well, the total area in the tails must be 0.32. But because it's symmetric, we have to split that in half, right? So the total area in the tails must be 0.32. But because the curve is symmetric, we know the area in one curve, or in one tail, I keep mixing those up, in one tail must be 0.32 divided by 2, 0.16. Clean that up. Cool. Great. So we can check that, right? We can say, okay, well, if this area is 0.16 and this area is 0.16, we can double check and make sure that this adds up to 1, right? And so we have 0.16 plus 0.68 plus 0.16, it is 1, right? So we've got all our areas covered. Okay. Nice. So then, if I say, okay, what's the probability of finding something larger than this? Okay, so we found an observation, just to recap, that is 1 standard deviation below the mean, right? So it's at mu minus sigma, whatever mu is and whatever sigma is. So we found an observation, right? Again, that's here. That's the one we're talking about. We said that the probability of finding something smaller than that, right, was 0.16. What if I asked you, what's the probability of finding something larger than that? So what is the probability of finding an observation larger than this? Probabilities, remember, is the area under the curve, right? So really what I'm asking is what's the area under the curve above this point? Okay. So we have a couple of ways already that we can find this, right? We could use the fact that the total area under the curve is 1, and that we know that this area is 0.16, right? Or we could say, well, it must be 0.68 plus 0.16. I think you'll find that they're the same, right? So, oops. We have 2 ways of finding this. First one is to say that the total area is 1. And the area below this point is 0.16. So area above must be 1 minus 0.16. 1 minus 0.16, 0.84. Or our second option is that we can add the central 68% or 0.68, I'll say, the central 0.68 with the upper tail of 0.16 to find that 0.68 plus 0.16 0.84. So what we need to get comfortable doing is thinking about each of these pieces as a puzzle piece, and then whichever way you want to cobble together a probability is fine, right? If you like to do, okay, so I know the area in the tail, in the lower tail is 0.16. I know the total area is 1. That's probably my go-to, right? Or if you want to look at these pieces and say, okay, well, if I want this area above here, and I know this one is 0.68 and this one's 0.16, I can just add them together, right? And so we'll get comfortable working with these, right? And so it behaves the same way for if we move out 2 standard deviations. 2 standard deviations, remember we have the 68, we have it here, the 68, 1 standard deviation, 95, 99.7 rule. Okay. So we can draw it out. So the 68, 95, 99.7 rule. Oh, sorry. Is that good? Okay. Sorry. So if we have our normal distribution, mine's looking a little wonky. It's okay. It's still centered on mu, right? And putting in our tick marks at mu, minus, and plus 1 sigma, 2 sigma, 3 sigma. Right? So here, mu minus sigma, mu minus 2 sigma, mu minus 3 sigma, mu plus sigma, mu plus 2 sigma, and mu plus 3 sigma. So I'll do it below here, right? Because we've got the central 68% between the first two ticks, right? So here, between here and here, we've got 68% of the curve. Then between mu minus 2 sigma and mu plus 2 sigma, we've got the central 95% of the curve. And then finally, between mu minus 3 sigma and mu plus 3 sigma, we've got the central 99.7% of the curve. So within 3 standard deviations, we've covered a lot of the probabilities already, right? 99.7%. We still have a little bit of area in the tails, right? So find the area in each tail. In each tail, not captured, right, or outside, but not captured by the plus minus 3 sigma, right? Meaning 3 standard deviations on either side, right? What's the area in the tails there? So we know that the total area is 1. And the area captured is 0.997, right? 99.7%. So total area in the tail, so total area in the tails, right, must be 1 minus 0.997. .003. Careful with your zeros. So 0.3%, that's tiny, right? And then as a decimal, 0.003. And then that's split up between the 2 tails. Right? Then this area is split evenly amongst the tails. So each tail must be 0.003 divided by 2, 0.0015. Right. Or 0.15% if you want to. Okay. So just really, really tiny. So even though these tails go out to infinity, right, and they never close, right, the total area in there is only 0.15% in either tail, right? So very, very unlikely that anything happens in the tails. Okay. This tells us it is very unlikely to see something beyond mu plus minus 3 standard deviations, right? Because the probability of ending up in the tails on either end, right, is very, very unlikely. Possible, but not likely. And so I'll say that someone measuring 8 feet tall, right? They would end up way out there. Very unlikely to find someone that's 8 foot, right? But possible, I guess, right? So unlikely, still possible. So in general, as a rule, we actually say anything beyond 2 standard deviations is going to be considered kind of extreme. Okay? So we don't go as far as 3 standard deviations. Once we hit 2 standard deviations, we say, oh, that's kind of unlikely to see something like that. Okay? So as a rule, we will say anything beyond 2 standard deviations on either side of the mean will be considered extreme. Will be considered extreme. Potentially. Yeah, we would probably call it an outlier. Yeah. Mm-hmm. So now, right, we have this idea of extreme values. So our goal in this course is to be able to say that, okay, well, given my information about the population and my data, right, and I found this point, I can say that it's extreme because the probability of seeing something this small, for example, right, is very unlikely. Right? So we have a pretty good idea of this stuff, right? If I tell you, oh, I found an ant and it was 5 centimeters, I think you automatically say, whoa, that's huge, right? You would say, whoa, that's so extreme. Whoa, the probability of that is so small, right? Same idea. Okay. So we're talking about how many standard deviations is something from the mean, right? So we need to develop a way to calculate that. So just as a quick example, we need to be able to calculate how many standard deviations an observation, we're going to denote it by X. So an observation, just any observation X, is from the mean. Bless you. Okay. So for example, if I say, okay, I'm going to tell you that the mean is 6 and the standard deviation is 2, X is 4, right? I want you to draw out this curve. So for all these problems, we're going to find it very helpful if we just draw out the curve. Even if it doesn't make sense to you now, right? I want you to get in the habit of doing it until it clicks. Okay. So drawing out the scenario here, right? We can draw our normal distribution. I know it's centered on mu equals 6, right? And down below, I just have a normal number line, right? Anything below 6 is going to go below 6. Anything above 6 is going to go above 6, right? And so what I'm going to do is I'm going to draw out my X equal to 4, So somewhere here, I have x equal to 4. Okay. And I want to know how many standard deviations can I fit in here? Well, if a standard deviation is worth 2, right, then I go just from mu minus, so from mu equals 6 down to 2, well, I'm just 1 standard deviation below the mean, right? So here, an observation of 4 is 1 standard deviation below the mean. Yeah. I will be. Oh, because I said that sigma is worth 2. Right, so I'm asking how many sigmas can I fit in here? Right, so then exactly, I found the distance between 6 and 4. And then I take that distance and I divide it by what a sigma is worth. Right? But this one, it's kind of like, yeah, nothing groundbreaking, right? But what if I said something like, how about another example? What if I said that mu is still 6, the standard deviation is still 2, but now I have an observation of negative 4.91. Now what? Right. So we can draw it out again. Right? So we draw out our curve and we have this normal distribution here. Still centered on 6. I'll say mu equals 6. And somewhere below it, we have a negative 4.91. Okay. I'll put it a little bit further out here. Doesn't matter. X is negative 4.91. Well, so we have 6 here, and then at some point here, we have 0. I'll get rid of that. Huh. Yeah.
So is X always on the left side?
No, not necessarily. Yeah, just in this case, yeah. I didn't get too creative, I guess. Yeah, so X can go anywhere on the line. Yeah. Okay, so now how many standard deviations is X equal to negative 4.91 from 6? If we had to work this out, right, and we can, I think you would start by saying, okay, I'm going to find the distance between negative 4.91 and 6. Right? And so first thing we're going to do is find the distance between negative 4.91 and 6. So we're going to go 6, or sorry. Yep. Negative 4.91 minus 6. the distance between negative 4.91 and 6, which ends up being 4.91 negative plus, or sorry, minus 6, negative 10.91. And we can check that, right? You can look at this and say, oh, okay, yeah, that looks reasonable. So I have to go from negative 4.91 to 0, and then I have to go a distance of 6. Sounds reasonable. 10.91. The negative is just telling me that I'm below the mean. So then we're going to find how many standard deviations we can fit into negative 10.91. So then we take negative 10.91 divided by 2, right? A standard deviation is worth 2. So I'm just seeing how many times can I fit 2 into 10.91. I get negative 5.455. So this tells us, so x equal to negative 4.91 is, and I'm going to drop the negative because I'm just going to say is 5.455 standard deviations below the mean. So the negative is just telling us that we're below the mean. Positive would tell us that we're above the mean. Okay. Is 5.455 standard deviations below the mean. Right. Negative means below. Positive means above the mean. Well, okay. So from here, we've developed the Z calculation. So Z is a standardized value, right? And so Z tells us how many standard deviations something is from the mean. Okay. So from now on, we will calculate Z, to find how many standard deviations X is from the mean. Oops. And on your formula sheet, right, you have Z is X minus mu over sigma. And if you have a look at this, this is exactly what we did, right? We took our negative 4.91, that's our observation X, minus our mean of 6, right? So minus mu. And then when we found that distance, we divided it by 2, which was our sigma, right? So Z, we call a standardized value because it just brings all our points down to the same scale, right? How many standard deviations is it from the mean? Right? So we call Z, a standardized value, as it tells us how many standard deviations an observation X is from mu. I'll throw in standard deviations and then in brackets here, sigma. An observation X is from mu. So this is going to let us compare things from two different populations, right? If you find a girl that's 6 feet tall, right? How does that compare to finding a man that's 6 feet tall, right? To their distributions, right? So standardized values, or what we're going to call Z scores, allow us to compare observations from different populations, right? From different populations / distributions. So even if you have different means, different standard deviations, right, you can standardize values to compare them, right? And next day we'll talk about, I think there's LSAT and SAT scores, right? They're scored on different levels, right? But if you scored this on the LSAT, or not the LSAT, what is it? The American ones. There's the SATs and ACT, thank you. Like the LSAT, you don't write that in high school. Like if you did, good work. Yeah, so thank you. ACT and SATs, right? They're scored on different levels, right? But you can compare scores. So I wrote the ACT, you wrote the SAT, who did better, right? We can compare those by standardizing our values, right? And seeing, well, I was 2.1 standard deviations above the mean and you were 3 standard deviations above the mean. So compared to your group, you did way better than I did, right? So, so that's the whole idea of standardizing. But we'll do some practice before we get there. So let's do a little example. I'll just say find the Z score of X equal to 7.32 if mu is 6 and sigma is 2. On your formula sheet, right? Now we're just going to go straight to our formula sheet. Actually, let's map it out first. All right, let's see what we've got going on here. So we've got a normal distribution with a mean of 6. And I have an observation of 7.32. 7.32 has to be somewhere above. And I know people like to spend a lot of time figuring out where this 7.32 would be. Oh, it would be really close. No, this is all just to visualize what's going on, right? So I just need to show that 7.32 is somewhere above the mean, right? And then I can just draw it where it's convenient and nice to look at, right? It doesn't actually matter. Okay. So if we have to calculate the z-score, z is x minus mu over sigma from your formula sheet. So z must be, x is 7.32. X is always your observation, right? So it's the line that you drew after you drew the mean. So first thing you're going to do is draw the mean, right? That's your mu. And then whatever observation that we're interested in, that's your second line. Okay? So 7.32 minus 6 over sigma, which is 2. So we do 7.32 minus 6. This distance is 1.32 divided by 2. We have 0.66. Meaning this observation, 7.32, is only 0.66 standard deviations above the mean. What if I asked you, what's the probability, what's the approximate probability of finding an observation larger than 7.32? Okay, just approximately. Okay. What is the approximate probability of finding an observation larger than 7.32? Okay. So we can ballpark this, right? And so I'm going to draw out my curve again here. I know I'm still centered on 6, and I have this observation at 7.32. Now I'm asked to find the probability. Probability is the area under the curve, right? And so what's the probability of finding something larger than 7.32, right? So I'm going to shade in the area that I'm looking for. Okay? So here I'm going to find this. If we drew this, right, and we said, okay, so from the mean, I know that between mu plus sigma and mu minus sigma, so if I had moved out a whole standard deviation, right, in between here and here, I would have 68%, right, or 0.68. Okay. But we found our observation was somewhere here, right? We're at mu plus 0.66. Because that's what our Z told us, right? Our observation translates to mu 6 plus 0.66 standard deviations, sigma. if I asked you to find, right, this area, right, the area above Z of 0.66, right, Z of 0.66 is easier to say than mu plus 0.66 sigma. Okay. So this here is Z of 0.66. So we want to approximate the probability. So approximate the area above this line. Right. I only know the areas above mu. We only know the area above mu. What's the area above mu? If the total area is 1 and it has to be symmetric, then the area above mu must be 0.5, right? Or 50%. Right? 50% of the curve is above mu, 50% is below it. Right? So we only know the area above mu is 0.50. And we already talked about it, right? You can go through and calculate it again, but I'm just going to use it. And the area above mu plus sigma we said it was 0.16, right? We said the central 68%, and then we had 0.32 left over, split evenly amongst the tails, right? So it must be 0.16. It's a pretty big range, but that's as close to our approximation as that we're going to get. Right? So just zooming in here.
Sorry, how did you get the 0.16?
Oh, I'm stealing it from earlier when we developed it and said, okay, well, between mu minus sigma and mu plus sigma, we've got the central 0.68. So to find the area in the tail above that, right, we have 0.32 left over, split evenly amongst the tails, 0.16. So now, right, we know that here at mu, okay, and I'll move out mu plus sigma to make a little bit of room. Right? I know that this area is 0.5 and this area is 0.16. And my observation, let's throw it in somewhere here, is at mu plus 0.66 sigma, right? Which is the same as, or Z equal to 0.66. Right, Z of 0.66 tells us that we are 0.66 standard deviations above the mean. Right. So those are the same thing. So we'll quickly gravitate towards working with just Z's, right? Instead of mu plus 0.66 sigma, right? That's a lot. Yeah. You're probably not happy with this approximation, but this is as good as it's going to get, right? The probability of finding something larger than this, or 7.32, I think we were working with, right, is between 0.5 and 0.16. That's all we know. Right? Therefore, the probability of finding an observation larger than 7.32 must be somewhere, probably closer to 0.16, right? But is between 0.50 and 0.16. I know it's larger than 0.5, right? But I also know, sorry, it's smaller than 0.5. Why am I correcting myself? Here, because I moved out here, right? So it's smaller than 0.5, but larger than 0.16. Okay. Must be smaller than 0.5 and larger than 0.16. Okay. Because we're talking about the area in the tail. Right? So I know at this point here, right, if I know that this point is, the area in the tail is 0.16, well here, my area must be larger than 0.16. Right? But here, right, I know the area in the tail is 0.5, but I actually have less area than that there. Right? That's a little whimsical. Okay. So before we go, I just want to talk about the Z distribution. So Z distribution is its own thing. And like we said, Z just shrinks down any population to a standardized scale, right? And so Z shrinks any normal distribution to a standardized scale. Okay. And Z has the following distribution or characteristics, let's say. Following characteristics. First one, Z follows a normal distribution. So Z follows a normal distribution. Makes sense, right? It's taking stuff from a normal distribution and shrinking it down to a standardized scale, right? So it's going to follow the same distribution. Z always has a mean of 0. Z has a mean of 0. Why is that? How far from the mean is the mean? 0 standard deviations away, right? And so you shrink it down and now it's centered on 0. Okay. And Z has a standard deviation of 1. Right? If you've moved 1 standard deviation away from the mean, right, your Z is going to be 1. Right? Okay. So that is good for today. Enough to forget over the long weekend. I'll see you on Wednesday, I guess. All right. Have a good one.